What?
So is this everything there? Do we have a couple sections?
No, we only have one section to do today, and it's on permutations. And then as we're going through this material, you'll probably feel like it's kind of difficult, but the homework I require of you is not that much.
So next week's the review now.
So next week we will do the chapter 5. We'll do the chapter 5 test, and then we'll spend the second part of class doing any review that you guys want to do. And then the week after that we'll have the midterm, which, what did they say, was 15 problems, so roughly twice the size of the test you've been doing.
That'll probably take a whole class.
Yeah, so that should take the whole class period, and then after that, done.
Do you
For the semester.
use just questions off of other tests for the midterm?
I use questions, so they could be homework questions or previous test questions.
Okay.
So that's what it is. And then I'm pretty sure that the extra credit question on there is prove the binomial theorem using proof by induction.
Great.
So you can prepare yourself for that.
I'm going to try it. I really wanted to do it last time.
All right. So before we start talking about permutations, let's just get up to date on vocabulary real quick. Remember what all our words mean. First off, what's a relation?
Set of ordered pairs.
Just a set of ordered pairs, right? And then what's a function?
A relation from one set to another.
No. A function is a relation where every left-hand element has a unique right-hand element.
Okay.
I can't have 1 goes to 2 and 1 goes to 3. One can only go to one thing. Does that make sense? So that was a function. Now we had the notion of a one-to-one function. What's a one-to-one function?
For every element, well, just one element,
Right, it goes both ways. So one way you can say it is it's a function whose inverse is also a function. That's a pretty standard way of saying it. Another way you can say it is for every right-hand element, there's a unique left-hand element. So every left-hand element has a unique right-hand element, makes it a function. Every right-hand element has a unique left-hand element, makes it a one-to-one function. And notice when we take the inverse, we just swap
right?
those.
So it's kind of, there's no repetitions in the domain or the image.
Sure. Yes, that's one way you can think about it.
And then everything in the left has to map to something, right? No, is that right?
Well, we weren't talking about function from a set to a set.
Oh, right.
We were just talking about a set of ordered pairs. And now we have the notion of f from A to B. When we said f from A to B, f was a function whose left-hand element is the set A, and whose right-hand element is a subset of B. Remember that? And we said f was on 2 if it used every element in B. Good with all that? All right. And then also, when we had a function from A to B, we had the notion of what was I just lost a word. I have it right here. A bijection. Geez. When is f a bijection?
It's on 2 and 1.
When it's one-to-one and on 2. So if f is one-to-one and on 2 from a set A to B, then we call it a bijection. Okay? So a bijection is a special type of function. Today we're going to be talking about a permutation, which is a special type of bijection.
If the inverse of a function is a function, then it has to be a bijection, doesn't it?
If the inverse of a function is a function, and you have a function from A to B, then if its inverse is also a function, then yes, you have a one-to-one and onto function.
Right. So you can't, what I'm saying is you can't have an inverse that's 1-to-1 but not on 2.
You can, but not if you're talking about a function from A to B.
Oh, okay.
Right? So the only time that we're guaranteed that f is a function from B to A, f inverse is a function from B to A, is if f was one-to-one and on 2, and that was a proof we did.
Right.
Okay? So now we're talking about a permutation, which is a special type of function. And it's a type of function where the domain and the codomain are the same set. If f is a bijection from A to A, we call f a permutation on A.
Okay.
So that's where we're beginning, a permutation. So let's just, sorry, ignore this. That's the side up for my calculus. Okay. So permutations. Definition. Given a set A, a permutation on A is a bijection from A to itself. Nice and simple. As a matter of notation, we typically use Greek letters when we're representing a permutation.
Is there a reason for that?
Just so it's obvious to your brain, right, when you're looking at it, hey, we're talking about a permutation. Same reason we use like n when we're talking about natural numbers. Same reason we use f when we're generally talking about a function. So if I see f, then I say, oh, all I can assume is that this is a function. When you see pi, then you say, okay, I'm talking about a permutation. So it's just to help your brain make those links, do little sanity checks as you go. So let's just look at an example of a bijection, or not bijection, a permutation real quick. So let's say A is a set 1 through 5. And we have pi, a function from A to A, given by this. 1 goes to 2, 2 goes to 4, 3 goes to 1, 4 goes to 3, 5 goes to 5. That is a permutation. Now, you might have heard the word permutation before. I don't know, have you?
Yeah, last year.
How many permutations can you get is the same way as asking how many orderings can you make.
So it's like combinations, but you don't have to divide by anything.
It's kind of like combinations. Permutations is how many different orders I can place these things in. And we've already done problems like this. How many different orders can I place these 3 things in? 6. I have 3 options for which one comes first, 2 options for which one comes second, 1 option for which one comes third. And then the difference with combinations is you can repeat elements.
Right.
So permutations, there's no repeat, you're just rearranging some objects. Right?
Okay.
That's exactly what a permutation is meant to capture here. The idea of rearranging objects. So we took the objects 1, 2, 3, 4, 5, and we gave them the order. The first object is 2, the second object is 4, the third object is 1, the fourth object is 3, and the fifth object is 5. Or in other words, we're saying 2, 4, 1, 3, 5. This is a reordering of 1, 2, 3, 4, 5. So that intuition for counting that intuition for the number of ways objects can be arranged as a permutation is exactly the idea that this captures. There's a reason that's the name.
So we'll probably be doing a lot of counting permutations then. Counting how many permutations you can make on a set?
You've already been doing counting with permutations.
Okay. What do you mean?
We've already had you answer questions like, if I have the set 1, 2, 3, how many functions can I make from this set to this set? Oh, that's not the same. That's combinations. I don't want to teach you that. I should say that.
Okay.
But that's all a permutation is meant to capture the idea. It's a reordering. And you'll see that there's a lot of cool stuff that we can use permutations to represent. But fundamentally, you should already be familiar with this notion of using a permutation to do an ordering, and that's exactly what this is. Because every right-hand element is going to come up exactly once, and every left-hand element is going to come up exactly once. Right? So if I were making a permutation, I have 5 options for how to fill this out. Now I only have 4 options for how to fill this out. Now 3 for this, now 2 for this, now 1 for this. I'm deciding which one goes first. I pick which one goes first. Now I can't use that again. Notice if I tried to use one again, I no longer have 1-to-1, or I might not have on-to.
Right.
So it has to be a bijection. Once you create a bijection from a set to a set, it's the same thing as thinking, how many ways can I finish that? And how many? So I have 5 options right now for that. I say, okay, we'll make that 2. Okay, now I have 4 options for that. Make it 4, make it 1, make it 3, make it 5. 5 options there, 4 options there, 3 options there, 2 options there, 1 option there. Or in other words, over 5 factorial ways, I could have made this. So there's 5 factorial permutations on this set. There's 5 factorial ways I can order the elements in this set.
Right.
Okay. So, idea of a permutation. Now, let's talk about all the permutations on the set. So given a set, 1, 2, 3 to n, the set of all permutations, all those bijective functions on that set, we denote S sub n. So back to when we were talking about A had 5 elements, so we know there were 5 factorial permutations we could make here. There was 5 ways I could finish this element, then 4, then 3, then 2, then 1, right? So S sub n here represents all the permutations. It's the set of all those functions, the set of all permutations on this set. Make sure that makes sense because this notation's not going away. So if I'm talking about S sub 3, or in other words, all the permutations on the set, 1, 2, 3, and no further, how many are there? How many are in there? 6. So let's make sure that we understand this exactly. I need 1 to go to something, I need 2 to go to something, and I need 3 to go to something. We're saying how many permutations when n is 3? N is how many elements we go up to. If we go up to 3, how many permutations are there when we have 3 elements? There's 6. That make sense?
Yeah.
Okay. So S of n denotes the set of all possible permutations on this n element set. That's what it denotes. That feel like that make good sense? Okay. Now there's a special permutation on a set, which is, we've already talked about it before, the identity function on that set. The identity function is a permutation. The identity function is one that maps 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, etc. So we use the Greek letter iota, which is just like the lowercase I without the dot above it. We use the Greek letter iota to signify the identity permutation. So iota is 1, 1, 2, 2, 3, 3, all the way to n. Does that make sense?
It doesn't have to be 1, 2, and 3 though, right? It could be any elements that are in that set.
So we're talking about a very special set here. So we're first talking about the set of elements 1, 2, 3 to n exactly.
Oh, okay.
S sub n denotes the permutations on this exact set.
So it has to be 1 through something to n.
Yes.
It can't be negatives, it can't be 0.
Correct.
Okay.
So we're talking about a very specific set that we're taking permutations on, and a very specific set of permutations, and then the identity element in there we designate iota.
Okay.
All that coming together? Okay, so now let's talk about some properties that this set has, S sub n.
So I do have one question. How do you denote the set of all permutations on a different set? Is there a way to do that?
Well, you can always just say let this be the set of all functions from A to B. I mean, we've already used verbiage like that in the past lecture.
Right.
We said, how many functions can I make from A to B? Where A and B were in sets. Right? So there is no special shorthand, at least that we're interested in. Obviously, if you were doing your own thing, then that came up a lot. You'd probably come up with a shorthand. But this S of n, she just wrote this whole thing, so I may as well create a shorthand. So let's talk about some of the properties of S of n. First property we already noted is the cardinality of the set. Cardinality of the set S of n is n factorial, which hopefully makes perfect sense. And then let's talk about some other interesting properties. Given two permutations on S of n, the resulting permutation, given two permutations, the composition of the two permutations is also a permutation.
Wanna give an example of that?
So one way of saying it would be,
I
if this is a bijection and this is a bijection, then the composition of those two is a bijection.
Okay. Yeah.
So
Yeah.
first off, keep in mind, the domain of this thing is the domain of this thing is just a set, 1 through n, right?
Right.
And the range of this thing is the range of this thing is a set 1 through n. So we already know that this is a function from this set to this set.
We're not going to prove that.
Now, so this was already, I don't know, was it a homework problem? To prove that the composition of two bijections is a bijection?
I don't think so. I didn't do one like that.
It was prove the theorem. I don't remember exactly. It might have been.
So this property, this property, this property, and this property should have all already been covered in either problems I assigned to you guys or I screwed up. And that's not good that I didn't catch that last time.
I don't remember anything like that.
Okay, so let's think through to make sure it makes sense.
Well, I mean, it makes sense, but I'm just wondering if you're going to prove it.
Well, you can see that the domain and the codomain are the same, are from this set to this set. So it satisfies that property, right?
The codomain's just the.
Sorry, this set, the right-hand set. What did I say before? So the domain and the codomain are both the numbers 1 through n. So it satisfies that part of being a permutation. Now the second thing is to make sure it's a bijection. To make sure it's a bijection, I mean, you kind of logic through it.
It has to be bijection.
Yeah, this is going to map 1 to some unique output here, to some unique input here, to some unique output here. So 1 can only be mapped to one and only one thing.
Okay.
Oh, here's a real simple way of saying it. Both these are functions, so their composition is a function.
Okay.
The inverses of both these things are a function, so their composition is a function.
Okay.
So this function and its inverse are both functions, so it's 1 to 1. And that's already on to, which was the first thing we talked about.
Okay.
So there's an easy way to show that that's a bijection. That make sense? So that's not actually that part of proof. Okay. Next is one that I'm pretty sure we proved in class last time. If you give me 3 bijections.
What's the third term?
Oh, now you made me lose it, right? I couldn't say it.
I've seen it very stupid.
Yeah, so pi, sigma.
Is that theta?
Now
What's all theta? Is theta right through the middle?
the
Why are they so
tau.
so
There we go.
similar?
Tau. It's tau. So pi, sigma, tau. Okay. So if I have 3 permutations, pi, sigma, tau, then pi composed with sigma composed with tau is the same as pi composed with sigma composed with tau.
Yeah.
So in other words, composition is associative.
Yeah.
And we did prove that last time.
Yeah.
Okay. Next one, up here. Given some permutation, that permutation composed with the identity is equal to the identity composed with the permutation is just equal to the permutation. We did that one, I'm pretty sure, right?
Yeah.
And then finally, for all permutations, pi, for all permutations pi, its inverse is a permutation. The inverse of a bijection is a bijection, right? So that makes perfect sense. So for all permutations in S of n, its inverse is also an S of n. And then pi composed with its inverse is equal to its inverse composed with pi is equal to the identity function.
Right.
Those just undo each other. Okay. So those are some interesting properties that this set has, some nice properties. Good? So now let's think about some other ways that we can visualize these permutations instead of just thinking about them as sets of ordered pairs like that. It's not a very useful way to think about it, and it's kind of a verbose way to think about it. So one of the ways that we can think about pi here, so pi is just this permutation. I think I wrote the exact same thing I wrote over here. So pi is just this permutation. Here's another way that we might want to write it down to help us see what's going on. The top row is the left-hand elements. The bottom row is the right-hand elements. So 1 goes to 2, 2 goes to 4, 3 goes to 1, 4 goes to 3, 5 goes to 5. Right? Now notice that the top row, anytime I write a permutation this way, the top row is always just going to be 1, 2, 3, 4, 5.
Yeah.
So that's kind of redundant information. So I could just write it this way. The first thing is whatever was paired with 1. The second thing is whatever was paired with 2. The third thing is whatever was paired with 3. The fourth thing is whatever was paired with 4. The fifth thing is whatever was paired with 5. Captures the same information, right? One more useful way about thinking about these things to capture the information that we care about and not lose. The point I'm making here is there's more concise ways that we can write this without losing information, right? If I gave you this, then you know how to reconstruct this and get all the information back. That's what I mean by that. So that's the nice thing about notation. Notation captures all the information with less writing. So that's one of the things that we're interested in. When we want to examine permutations, we want to be able to talk about it quickly instead of having to write out this big, humongous thing every time we want to talk about it. One of the second ways that we might want to write them out is just state what each one goes to in order. So that sounds bad, but here's what I mean. So this is called cyclic notation, and here's how you write it. So you start with 1, and then the thing that goes next to 1 is whatever 1 goes to. So 1 goes to 2, so write 2 next. Now what does 2 go to? 2 goes to 4, write 4 next. What does 4 go to? 4 goes to 3, write 3 next. What does 3 go to? 3 goes to 1. Oh, that completes that cycle. Now come over here. What's next? We haven't used 5 yet. What does 5 go to? 5 goes to 5. That completes it all. So looking at this picture might be, looking at this picture and looking at this helps you understand cyclic notation.
Like a set containing those, or is it written like that?
It's written exactly like this.
So you could have a bunch of cycles.
Yeah, you can have way more than 2 cycles. But looking at this function, if we drew like a picture of what everything goes to, here's a picture. 1 goes to 2, so let's put that arrow in. Here's 1, here's 2. 1 goes to 2, that arrow's in. 2 goes to 4, put that arrow in. 2 goes to 4, there it is. 3 goes to 1, put that arrow in. 3 goes to 1. 4 goes to 3, put that arrow in. 4 goes to 3. And then 5 goes to 5, put that arrow in. So you see how you would create this graphic from this
Are those
permutation?
graphics useful for reasons other than just understanding how? what it
Yes,
looks
very much so.
like? What do you use?
Well, we'll see a proof that we're going to do with them when we get over there, but immediately, unfortunately, we're not doing the next section, which is getting into symmetries, but it's useful in symmetries. So one of the questions you might ask is, if I've got a square, how many ways can I lay out that square so you can't tell that I changed it? How many different arrangements are there?
Okay.
And those are called, those would be different symmetries.
It's just 4, right?
Now, there's 8. There's 8. Yes.
Okay.
So,
Oh, okay. Yeah.
it's useful for that, but we'll see it in action here. But this is just, appreciate for a second how different this is from the idea of a function. Or a permutation, an ordering of things. So this captures all the same information as reordering objects does. Never mind. I don't want to push that point. Anyways, so you know how to go from this to this graphic, and then this is capturing the exact same information as this graphic. It's the same way of writing this permutation. And it's called writing it in cyclic form.
Both of those?
This is writing it in cyclic form.
What about the other?
This is just a graphic to help you see it. It's just a graph representing the permutation.
Is that just, would you call it matrix form?
Oh, up here?
Yeah.
I'm not sure if that really has a name. Just helping you see what's going on.
Okay.
But this is a very common way to write permutations, cyclic form. So once again, you start with the lowest element.
Why that way particularly? It seems like the other way is just as effective.
This way?
Yeah.
Because this tells us right out the bat, like this visualization. Now I can see this visual and I know what everything goes to.
Oh, okay. Okay.
So now I instantly know, well, this permutation has 2 cycles. Does that make sense? And you also get all the information that you had before. So let's do a more convoluted one and let's write it in cyclic notation and make sure it makes sense. So here's our permutation pi. 1 goes to 2, 2 goes to 7, 3 goes to 5, 4 goes to 6, etc. And let's write it in cyclic form. So we start with 1. What does 1 go to? 1 goes to 2. Okay. What does 2 go to? 2 goes to 7. Okay. What does 7 go to? 7 goes to 1. That's back where we started. That closes the loop. So that's 1 cycle. So now we start our next cycle. We look for the smallest element we haven't used yet. That's 3. What does 3 go to? 3 goes to 5. Okay. What does 5 go to? 5 goes to 3. That completes the cycle. Start our next cycle. What's the smallest element we haven't used yet? 4. What does 4 go to? 4 goes to 6. Okay, what does 6 go to? 6 goes to 8. Okay, what does 8 go to? 8 goes to 4. That closes our cycle. And then 9 is a standalone cycle. So here's how you would write it out in cyclic notation. And then once again, here's a little graphic that goes along with it. Good with that? Okay. So, something I want you to notice, writing out pi verbosely, here it is. Writing out the same thing, 1 goes to 2, 2 goes to 7, 3 goes to 5, etc. When we take the inverse of it, the inverse of pi, we swap all the elements, right? So here's pi, here's its inverse. Now, let's fill out the table real quick. What does 1 go to?
7.
7. What does 2 go to? 1. What does 3 go to?
5.
5. What does 4 go to?
8.
What does 5 go to?
3.
What does 6 go to?
4.
What does 7 go to? 7 goes to 2.
Yeah.
Oh, you just have to look up here. And what does 8 go to?
6.
And then what does 9 go to? 9. So now let's write this one out in cyclic notation. So starting with 1, what does 1 go to?
7.
7. What does 7 go to?
2.
2. What does 2 go to?
1.
That closes our cycle.
Right.
Next cycle. Smallest element we haven't used is 3. What does 3 go to? What does 5 go to?
3.
That closes our cycle. Next, what does, let's see, 4 goes to 8, goes to 6, closes our cycle. And then 9. Okay, and then let's write our graphic real quick. Now we have 1 goes to 7, 7 goes to 2, 2 goes to 1, 3 goes to 5, 5 goes to 3, 4 goes to 8, 8 goes to 6, 6 goes to 4, and 9 goes to 7. Now notice what happened when we took the,
Yeah, that's interesting.
when we flipped it like that.
That's interesting.
What we essentially did is we flipped the direction on all these arrows,
Yeah.
right? And so, instead of writing it out like this, let me make sure my thinking right here, but I think we could have just looked up right here and switched the order that we wrote these in. So I think I could have just wrote 7, 2, 1, 5,
Doesn't it go?
3,
Has to go 1, 7, 2.
8, 6, 4, 9. So it doesn't have to go smallest to largest, that's just good convention. The only thing that matters is, does 7 go to 2, goes to 1, goes to 7? Does 5 goes to 3, goes to 5? Does 8 go to 6, go to 4, go to 8? And does 9 go to 9?
Yeah.
So let's see, did we get the same thing? What does 7 go to? 2. What does 2 go to? 1. What does 1 go to? 7. Yep, that's good. 5 goes to 3, 3 goes to 5, that's good. 8 goes to 6, goes to 4, goes to 8, yep, that's good. 9 goes to 9, yep, that's good. So rather than going through all the work of rethinking about this, the inverse is, just for each of those cycles, flip them. Flip, flip, and you've got the inverse, which is the same thing as switching the direction on those arrows. Good? Okay. Now, we're going to talk about a special type of permutation called a transposition. Now, this definition seems like a lot to chew until you understand what it's saying. That's actually kind of simple. So let's look at an example first. Pi here is a transposition because every element goes to itself except for we swap 2. So we only swap 2 elements. We did, so 1 goes to 1. So you start out with, let's just show you how you treat one. Start out with 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4. Okay? Oops, 4 goes to 4.
Okay.
Swap any 2 elements in the bottom, and you create transposition. So I pick 2 and 3 and I swap those. So now it's a 3 and a 2. It's like the simplest transposition you can, or sorry, it's like the simplest permutation you can get that's not the identity permutation, in other words.
Yeah.
It's a transposition. They're really simple permutations. So instead of everything going to itself, it's everything goes to itself except for 2 elements are swapped. That's what a transposition is. And now it's not giving sense of what I wrote over there, so let me redo the swap I did before. Let's see, I swapped 2 and 4.
Yeah.
So now let's wrap our head around the definition and see if we can make sense of it. A permutation tau in Sn is called a transposition provided that there exist 2 indices I and j that aren't the same index, such that it maps I to j and j to I, or in other words maps 2 to 4 and 4 to 2. So there, I'll mention the example as we go. So in our example, we swapped 4 and 2, right? So I'll read it with our example at the same time. So a permutation tau is called a transposition, provided that there exists I and j, 2 and 4, 2 indices, in the set 1 through n, or in our case 1 through 5, with 2 not equal to 4, such that tau at 2 equals 4 and tau at 4 equals 2. And all the other ones go to themselves, is what this is going to say. And that for all k in that set, where k is not the I and the j that we're talking about, then tau maps k to itself. So a lot to take in, but it's a real simple idea once you wrap your head around it, so make sure it makes sense.
Will you define indices?
Huh?
Will you define what the index is?
Oh, did I say index?
Yeah.
Sorry. Just 2 elements in this set. Count this one. We comment this thing count this one. Doesn't matter. So remember, what is the domain and the range of a permutation? It's this set.
Right.
1, 2, 3 up to n. So if there's 2 elements in the domain that aren't the same element, such that tau of the first equals a second, and tau of the second equals a first, and with all other elements of the domain mapped to themselves. Is the definition making sense? So all we're saying is we pick 2 and only 2 to swap. Everything else goes to itself. So the k's are everything that goes to itself, the things that aren't I and j. I's 2, j's 4.
You have to only have 2. You can't do 3 to swap.
Yeah, just 2 things swap. We're trying to make the simplest permutation that's not the identity permutation.
What's the point of that? Like, is there, what do you use it for?
We're going to decompose permutations into their transpositions. So instead of viewing,
I'm just wondering, like, what do you use to prove things? Is it just why? I mean, what's the reason we created the definition of a
So we can talk about permutations in terms of their transpositions. It's like the units of a permutation is the transpositions. Well, you'll see us use it again.
Okay.
So writing it in cyclic notation. So here's a transposition. We just swap the 2 and the 4. Everything else is the same, right?
Yeah.
So if we write it in cyclic notation, what does 1 go to? 1 goes to 1. That's it. What does 2 go to? 2 goes to 4. 4 goes to 2. That closes the cycle. What does 3 go to? 3. What does 4 go to? Oh, we already did that. What does 5 go to? 5. So here's what it looks like in cyclic notation. Now notice once again, if this thing's a transposition, all you care about is the 2 and the 4. You don't need the 1 there, you don't need the 3 there, and you don't need the 5 there. You already know that this thing's a transposition. So all you need actually is pi equals 2, 4.
Only if you know that.
If you know it's a transposition.
You have to know the set of transposition.
Yes.
You have to know what n is.
Yes. You do need to know what S of n is. But now we have this very shorthand notation for an entire permutation. Right? And once again, there's more ambiguity as to what we mean when we have parentheses with comma separate numbers. In this context, it represents a transposition. So, transpositions. Hammer says, every permutation I can split up into a composition of transpositions. It's like every number I can split up into, every natural number I can represent as a sum of ones, right?
Yeah.
I can take 5 and represent as 1 plus 1 plus 1 plus 1 plus 1. Any permutation you give me, I can take that permutation and I can represent it as a composition of transpositions. It's this transposition composed with this transposition, composed with this transposition, composed with this transposition.
Okay.
Does that make sense what I'm saying?
You're saying any 2 permutations. Well, you can make any permutation with the composition of your transpositions.
Perfect. That's exactly right. Maybe another way to say, another kind of equivalent idea would be like, think about prime numbers and multiplication. Every natural number greater than 2 I can view as a product of prime numbers. And I can break it up into its product of prime numbers. Similarly, I can take any permutation and break it up into its composition and transposition.
Every natural number is a product of prime numbers.
Greater than 2, yeah.
Okay, yeah.
Yeah.
Sorry, yeah. I don't remember proving that. I'm sorry, I had to.
No, we didn't prove that in this class. What is that? The Fundamental Theorem of Arithmetic or something like that?
I don't know.
That's a number theory thing. We might prove that in this class.
Difficult.
Not sure if we did. Anyways, so it's kind of that similar idea. Break it up into its like these fundamental components that are like as simple as we can get them. And there's not a permutation simpler than a transposition, except for the identity. But obviously, if you compose identities with identities, you just get out the identity. Right? You get some intuition for what these things are? So let's look at an example real quick. So I have pi is this permutation. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. Good?
Yep.
Now, let's break it up. Well, here's what I'm telling you. I'm telling you right out the door that this composition of transpositions gives me the exact same function. Gives me the exact same permutation. So that's, and I think you'll start to get a feel for this if we just flat out go through figuring out what each of these are. So let's figure out what 1 goes to, let's figure out what 2 goes to, 3, 4, 5. Not looking at this, but looking at this. And then we'll see how it produces the same thing. Okay? So when I plug in 1 to this function, what does it give me? 2. Then when I plug 2 into this function, what does it give me? 2. When I plug 2 into this function, what does it give me? 2. When I plug 2 into this function, what does it give me? 2. So when I plug 1 through this whole thing, 2 comes out. So 1 went to 2. Let's do the next one. What does 2 go to? Plug 2 into this, what does it go to? 2. No, 2 goes to 1. 2 goes to 1. And then plug 1 into here. 1 into here gives us
3.
3. 3 into here gives us
4. No. 3.
There's nothing changed in.
Sorry, my bad.
I know. These things are weird to deal with the first time you deal with them. That's why we're going through this mental exercise. Alright, let's restart 2. 2 plugged into here gives me 1. Plugged into there gives me
3.
Plugged into there gives me
3.
Plugged into there gives me
3.
So 3 comes out. Let's do the next one. 3 plugged into here gives me. Plugged into here gives me. Plugged into here gives me.
4.
Plugged into here gives me. Perfect. 4 plugged into here gives me. 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 And then 5 plugged into here gives me. 5 plugged into here gives me. 5 plugged into here gives me 1. 5 goes to 1. Which is exactly what this says. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. So those are in fact the same thing. Okay? And you can kind of see the pattern that we use there to get that. That's a common pattern to use to break a cycle up into its individual transpositions. The other way that we could have written this is the way I like better, is this is 1, sorry, didn't give me a lot of space here. This is equal to 1, 2, composed with 2, 3, composed with 3, 4, composed with 4, 5.
Composed with 5, 1.
Nope, that's it. So let's check this one and make sure it appeals to us. Let's plug 1 in. What does 1 go to?
1, 1, 1, 2.
1 goes to 2. Plug 2 in. 2 goes to 2, goes to 2, goes to 3, goes to 3. 2 goes to 3. And etc. So can you see the two patterns there?
Yeah.
So the first one we do this with this, composed with this with this, composed with this with this, composed with this with this. Except for I said that in reverse order, sorry. This is the first one, then we compose this way.
Yeah.
Because we compose right to left. So that composed with that, composed with that, composed with that, composed with that is what this is, right?
Okay.
And then this is kind of like, you compose those two, then those two, then those two, then those two.
Can you do it in a whole bunch of orders to get the same thing?
Oh yes. There's an infinite number of transpositions that would give me this exact permutation.
Infinite number?
There's an infinite number of different ways I can do this. Yeah, because I can swap back and forth as many times as I want.
Well, then those are the same. They're the same transposition.
Well, my point is I can compose as many on here as I want that just end up swapping and swapping back, swap them, swapping back, swap them, swapping back. Let me show you one more way to think about these transpositions. Let's see a place I can erase. Or I'll just do it over here in the marker. Another way that we get to think about transposition. So let's say I start out with a function. Let's only keep it a few elements. So 1, 2, 3, 4, 5. And then what do you want the mapping to?
Doesn't really matter. So 3, 5, 4, 1, 2.
All right, now let's apply some transpositions to these. So now I'm going to take this function, so we'll call this pi. Pi is equal to that. And now let's say I want to figure out pi composed with, other way. Pi, let's compose, what should we compose on there? Give me a transposition. 1, 3, and we'll compose on there 2, 5, and we'll do it like that for now. The way you think about applying these is just swapping those elements down here. So if this is pi, then pi composed with 1, 3 is going to look, I'll just write the output instead of writing the output and the input. It's just going to be 1, 5, 4, So that would be pi composed with that.
Yeah.
And if I compose that on there, that's swapping the 2 and the 5. So that would now be 1, 2, 4, 3, 5. Does that make sense? So every transposition I apply on there is like swapping 2 elements in the
You're trying to get it back.
in the domain. So the point is, I can sit here and swap back and forth all day, as many times as I want.
So how do we, like, if we go through it homework, make transpositions of it to make the permutation?
Right. So if you want to break a permutation up into its transpositions,
Yeah.
you can follow the pattern that we used right here. That works fine. You can follow the pattern that we used right here. That works fine. You can flat out, I don't know, take it by the horns and do the swaps that you want and calculate what you need to do as you go. You say, okay, I need to get this back. I need to swap the 4 into 3 places. So I'm going to apply the transposition 3, 4. And then when I apply that to this, I get the identity out.
Right.
So you can logic through it if you want. You can follow those tricks as general rules if you want. Anyways, so there's an infinite number of transpositions. There's an infinite number of ways that we can break a permutation up into its transpositions. There's not just a couple unique ways. But a pattern that we will notice is when you do break a permutation up into its transpositions, it's either always going to come out to an even number or an odd number.
Okay.
So that is a property that we'll have that we'll come across. But anyways, so here we go. There's 2 different ways of breaking up that permutation into its transpositions. Let's look at another example. So let's say that pi is this big old this big old permutation represented in cyclic form, right?
Yeah.
Now let's break it up into transpositions.
Okay.
And we're going to follow the pattern that we used up here.
Well, why does it go 1, 5, 4, 3, 2, 1 instead of 1, 2, 3, 4, 5? When you break it up?
Well, I can view it as 1, 2, then 1, 3, then 1, 4, then 1, 5. 1, 2, 1, 3, 1, 4, 1, 5.
Could you view it as 1, 5, 1, 4, 1, 3, 2? Right?
Here's what I view it as 1, 5, 1, 4, 1, 3, 1, 2. Now I'm not sure what you're saying. I'm saying, so there's 2 patterns here that we developed for how we can break this thing up into transpositions that works.
Okay.
So I can make my permutation those 2 elements, and then these 2, and then these 2, and keep working out. So that is one way I can do it. That's a common way to break it up.
Okay.
And then here was another one where you do those 2, then those 2, then those 2, then those 2.
Okay. I don't know why.
So maybe motivate the question a little bit. Here's the type of question you're going to get on your homework. Your homework question is going to be, break this up into transpositions.
Okay.
That's what it's going to be. There's a ton of ways that you could do that. I'm going to follow the same strategy that we used up here on the top line when we were breaking this cycle up into its transpositions. So breaking an entire permutation up into its transpositions, you can just break up each cycle into their transpositions and then compose everything together.
Right. Well, okay, so that makes sense.
So, breaking up this cycle, you do 1, 2, then 1, 3, then 1, 4, then 1, 5. Same thing we did up here. I don't know where I'm losing you. Did it make sense that we used these transpositions
Well, it made sense when we worked it out.
to represent that function?
So when we worked it out, yeah, that made sense. I'm now struggling with the fact that it works. I'm just trying to think of kind of why and
All right, let's
Why
just,
it's written that way.
let's go through it one more time. 1, 2, 3, 4, 5. Okay, 1, 2. This one says swap 1 and 2. So now, so we're starting with like the identity, and then to get this transposition, it would be 2, 1, 3, 4, 5. That's this transposition, right? 1, 2. That's the transposition 1, 2. Okay, now swap the 1 into 3.
Well, yeah, I see that it works. I mean, I realized it works when we did it the first time running. I guess a way that we could help is to go over ways that don't want to write it.
Well, you can't just write it any other way if you just try guessing.
Right.
Guessing something, it wouldn't work.
I don't even know where I'm missing it.
Well, okay, so what is a series of transpositions that in your mind should work that aren't those two?
I don't know.
It's not easy to just come up with one that works.
I know.
So I don't really know how to answer your question. Almost any series of transpositions you try doesn't work.
Right.
These are two that do work.
Right. There's going to be an infinite number that don't work.
Right. But there's also an infinite number that do work.
Okay, let's just move on. I'll probably get it.
Well, so if you can understand breaking up this cycle into these transpositions,
I know that working back, once that's already done, it makes sense and it works. When we see that cycle, I'm thinking, let's see, so it would be 5 goes to 1, 1 goes to 2, 2 goes to 3, right?
yeah.
So why, when we're doing this composition, we're going
Look, here's another way that we can view the same question. So it's like, I start with the numbers 1, 2, 3, 4, 5.
okay.
And you ask me the question, swapping 2 elements at a time, how can I get that to look like, let's see, what does this one's output look like? It looks like 2, 3, 4, 5, 1. Okay. So we have this, we need to get it to look like this. And I say, here's how you do it. Swap the 1 and the 2, then swap the 1 and the 3, then swap the 1 and the 4, then swap the 1 and the 5. And you did it. That's another way to do it. I don't know. Does that make sense?
Yeah, that makes sense. Okay.
I don't know. I'm now lost for
I think I'm good.
how to get that. Okay. So, same thing. So we had this cycle. We broke it up into these these transpositions.
Okay.
This cycle broke it up into these transpositions. The exact same pattern. This cycle broke it up into these transpositions, but what about this cycle?
Well, it goes to itself.
It goes to itself. So in all these transpositions, we just left 9 alone. So 9 still goes to 9. So pi equal to this in cyclic notation can also be represented by these transpositions. Now those brackets there are obviously not adding anything. I've just shown you that these came from the first cycle, these came from the second cycle, and these came from that cycle.
Okay.
Right? Doesn't matter what order you do those compositions in terms of their associative. So that's a systematic way that you can break up a permutation into its transpositions. So get a permutation, represent it in cyclic form, then you can represent it in terms of transpositions like that. It's a systematic way. So you should, anytime I give you a permutation, you should be able to know how to take it and represent with transpositions.
Okay.
Does that make sense?
Yeah.
That's a big part of what's going to be on your next test.
Can we
I'm going to give you like 10 permutations and say represent this with transpositions.
do a problem like that? I think I just need to go through it and figure it out.
Sure. Let's pick one over here. So, all this for a second. So you know how to go from pi as a permutation to pi in cyclic notation?
Yeah.
Right? That's just a different representation. You're good with going from here to here. Okay, so now let's represent this with transpositions. What's it going to be? What's my first transposition going to be? Well, my last one, if you want to think about it like that. Sorry. Let's think about the ones that we get from this cycle.
Why that cycle first?
It doesn't matter.
It doesn't matter.
Well, if the order matters down here.
Yeah, composition is commutative.
I'd have to think about that for a second now. No, it doesn't matter in terms of the bracket order, because we can change the order of these cycles and it doesn't change anything. So in other words, if I put this cycle in between these two cycles, it doesn't change anything. So order matters internally, but does that make sense?
Yeah.
Okay. Anyways, let's not bother with brackets. Let's just write it out. So I'm going to have 1, 7 composed with 1, 2. That takes care of this cycle.
Okay.
Same.
It's the same thing, so I don't know why it's not working. It's the same thing.
Okay, here's an easier parenthesis then, if that one's not good.
I feel like maybe it's
If you want to think about from left to right instead of right to left, let's think about it this way. 1, 2, 2, 7. How's that? So we could do this as 1, 2 composed with 2, 7.
Okay.
You like that way?
Alright.
So let's think about it this way.
Yeah.
Does that click it better?
Not really better. I mean, it makes it's the same. I mean, they're both.
Alright, so how do I write the next one?
Just 3, 5.
Just 3, 5. Alright, now here we go. What's next?
4, 6.
4, 6 works.
6, 8.
12, 6, 8.
8, 9, 9, which is
No,
just
leave it. That's it. This is not a transposition. Why is that not a transposition?
this is switching.
It's not swapping two elements,
Okay.
right? So that's it.
So
This is pi, this is pi, this is pi.
maybe it's just that it's abstract in my head, so I'm not visualizing it correctly when I try and do it. Because the process itself makes sense. Like, yeah, you're going to go 1, 7, and then 1, 2, and you're going to go 3, 5, and then you're going to go 4, 8, 4, 6. But it just feels like somewhere in there, I get I lose like what I'm doing. I don't know. It's weird. I'm trying to think of why, but I don't understand. Maybe it's just the notation is confusing me because it's so similar, like the cyclic notation and the transposition. They look pretty similar. Maybe that's throwing me off.
They do look real similar.
We can just continue now.
Well, make sure you know how to break into its transpositions.
Well, at this point, it's like I found the trick. The trick is you take this one and then you put it next to the one at the end, and the one next to the one at the end, and the one next to the one.
So you know the trick to break it up into its transpositions.
Yeah.
And you know how
I
to
feel like it.
plug it in to make sure you did it right.
Yeah.
Okay.
So I could do it like goes on and prop, but I don't feel like if I saw one, I could do it in a different way. That wouldn't be the trick.
Oh, that's fine.
Okay.
All right.
I feel like it's like I know the trick works, but I don't know why. Like I know when you plug it in, it works, but that's it.
You're just, remember, like the way I like to think about it is swaps. I'm saying, what are the steps I can use to make 1, 2, 3, 4, 5 look like the output of this thing, which is 2, 3, 4, 5, 1. What are a series of swaps I can apply to make that look like that?
You switch one.
That's the way I was thinking about it.
Okay.
And so you could come up with something on your own. You could ignore all this. You could just start looking at this and decide how you want to do it, right?
Right.
You can start with, oh, I want to swap the 4 and the 5, and then swap the 4 and the 3, and then you can keep going. And just write out what you're doing as you go. That's what these transpositions are doing. Swap one and the two, swap one and the
Okay,
three.
so that makes sense. I feel like it would get messed up when you do the composition stuff. So like, I think, hey, I want to switch the 5 and the 1. No, I switched 1 and the 2. And then the 2 and the 3. But it feels like somewhere in there it would get, I don't know, like it would get, there would be a mistake because, I guess that would work. I don't know. That's just
That's what you're doing. You're just rearranging it into the arrangement that you want. And the transpositions are the set of steps to do that. Okay. Something we've already talked about now a couple times. There's no one way to represent a transposition. Or there's no one series of transpositions I can use to represent a permutation. So here's a permutation. I can represent with those transpositions, with those transpositions, and with those transpositions. Every single one of those is going to give me the exact same permutation as that. Okay? And the thing to notice is 3, 3, and 5. They're all odd numbers. So this is what we would call an odd permutation. No matter what set of transpositions I use to represent this permutation, it's going to be an odd number of them. So while there is an infinite number of ways to represent a permutation with transpositions, there is some property that stays constant. Whether a permutation is odd or even is something that can be determined.
So are we going to prove that they can't be even? Yeah, you can have an even number and an odd number.
Yes, we are going to prove that. And I'm not going to prove that the way the book does. You can read how the book does it. They get into a big old 2-page conversation about some stuff that when you view it cyclically with the images, I think it's a lot cleaner and comes out better. So I'm not going to show you the long convoluted proof. Anyways, moving on. Okay. So exactly what I was saying before with even and odd. We call permutation even provided it can be expressed as an even number of transpositions. Otherwise it's called odd. We can represent it with an odd number of transpositions. So this was an odd permutation. This was an even permutation. Pretty simple definition there. Okay, here's a definition that's going to seem kind of weird. The sign of a permutation. The sign of a permutation is +1 if the permutation is even, and it's -1 if the permutation is odd. So SGN, sign permutation, right? Not sign like trig sign. I don't know. Maybe you've heard sign, but you haven't done sign.
That's different.
Okay, it's a different sign. Make sure that's clear. Completely disassociated from trig. The sign of a permutation is equal to +1 if the permutation is even, -1 if the permutation is odd.
That seems so arbitrary.
It does seem arbitrary, so I know that was going to feel really weird, and you'll see what we use it for, but
You might as well call it A and B. Okay.
But the point is, when you add evens with odd, well, I won't say it that way.
Okay.
So, in short, if pi is equal to n number of transpositions, then the sign of pi is -1 to the n.
Okay.
Right? So if n is even and pi is going to be 1. If n is odd, then n is odd here. And -1 to an odd is just -1. So does this make sense? Okay. So 2 different ways to think about the sign of it. We can view it as +1 if it's even, -1 if it's odd, or this is the way I like to think about it. It's just -1 to how many transpositions you have there. Okay.
Is there a notation for like you can use? There's a sum notation. Is there one for compositions like that? So instead of going tau sub 1, tau sub 2, all the way to the n, is there a way to just go?
I have never seen it if there is. But I wouldn't be surprised if someone's taking the time to do it. Because that's our real common thing. Is got what we mean by the sign of a function. Let's do a quick little proof. So if I have two permutations, pi and sigma, then the sign of pi composed with sigma is just equal to the sine of pi times the sine of sigma. Feel like you understand the question or the proof? What we're proving, I mean. So let's go through it real quick. So let pi be represented with A transpositions, and the sigma be represented with B transpositions. Then the sine of pi is just -1 to the A, and the sine of sigma is just -1 to the B. So then the sine of pi composed with sigma is equal to -1 to the A plus B is equal to -1 to the A times -1 to the B is equal to the sine of pi times the sine of sigma. Hopefully you're comfortable with that algebra.
Yeah, that makes sense.
Good there? Alright, that's the only trick in that proof. Other than that, it's pretty straightforward. Okay. Next proof using these graphics. I'm not going to do a full-fledged rigorous proof. I'm just going to help you see it in action and see why it happens the way that does, and then we'll continue. So, if pi and tau, why did I use tau? Oh, because it's a transposition. So, if we have a permutation and a transposition.
Is tau always used for transpositions?
No. So I should have specified why I did it. But it is common to use tau for transpositions. So, if we have a permutation and a transposition tau, then the permutation composed with the transposition has one more or less cycles. So I have some permutation with some number of cycles, like this thing. If I compose a transposition onto this thing, it's either going to increment the cycles by 1 or decrement the cycles by 1. It's going to either add a cycle or break a cycle. Okay?
Is that why that's plus 1 and minus 1?
We'll see the plus 1 minus 1 over here.
Okay.
So we'll come back to that question. But I'm just going to go with example to see it in action here. So one of two cases. So when you have a transposition, like 4-7, either 4-7 is going to be part of two different cycles on the permutation you're applying it to, or it's going to be a part of the same cycle you're applying the permutation to, right? Those are the only two cases.
Exactly.
So I have some permutation. Let's look over here for a second. Pick a transposition.
The transposition.
Yeah, give me a random transposition.
1, 7.
1-7. Okay, 1-7 will require the same cycle.
Yeah.
Give me another random transposition.
3, 5.
3-5. 3-5 will require the same cycle. Give me another random transposition.
6, 8.
6-8 will require the same cycle. Give me another random transposition.
1, 2.
Just pick any two numbers.
Yeah, okay.
1-9. 1 is part of this cycle, 9 is part of this cycle.
Why is there a transposition?
It's just a random. 1-9 is a transposition. I can just swap 1 and 9. That's a
You
transposition.
have to swap back.
Okay. What?
Sorry.
Remember fundamentally what a transposition is.
Okay.
What's transposition? We have, so in this case we're talking about through 9, right?
Yeah.
So we're in S sub 9. What's a transposition in S sub 9? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's the identity. Swap any two elements.
Right.
We'll swap 2 and 6.
Right.
6, 2. There's a transposition. 2, 6. 2 and 6 are not in the same cycles for this permutation.
Yeah.
So when I apply this transposition, when I apply a transposition to this permutation, one of two things is going to happen. Either the two elements of our transposition are going to be in the same cycle or different cycles.
Okay, what I was thinking was to make that permutation, we're going to take a transposition and like it.
No.
And then you
Okay.
have to switch it back.
Right. No. Just saying, applying a transposition to any permutation,
Right. Okay.
then either the elements of the transposition are in the same cycle or they're in different cycles.
Well, obviously.
Obviously, right. So, what we're going to show that is, if they're in different cycles, they end up combining those two cycles together to make one cycle. And that if they're in the same cycle, they end up splitting that into two different cycles. So in other words, here's the permutation, here's its picture, right? When I apply this transposition to it, so I compose this with pi, here's what comes out. Sigma, which broke the cycles. So instead of two cycles, now there's one cycle. Now if I take sigma and apply the same transposition to it, it breaks the cycles. It breaks one cycle into two cycles. So applying a transposition from here to here, or applying the transposition to this when they're in separate cycles gives us this. When they're in the same cycle gives us this. So that's the point that we want to pound home. So if my transposition, well, all we're really trying to say is it either added one cycle or it took away one cycle. Those are the only two cases. No, I used numbers, but we could have just used A and B instead. So I could have taken the time to write this out all generically and put A there, and then B over here. So you can't write this all out generically, just the notation gets kind of messy. So either way, it's the same idea. So now let's think about why, try to make some intuitive sense about why this combines the cycles. So instead of 4 going to 5 like it used to, so up here 4 went to 5, right?
Yeah.
So now when we apply this to it, 4 goes to what? In here 4 goes to?
Well, 5. Oh,
In here 4 goes to 7 goes to?
5.
Yeah, what does 4 go to in pi?
In pi goes to 5.
5. So plug 4 into this whole function now. This piece of it took 4 to 7. This piece of it took 7 to 5. Or 7 to 8. What did you say?
No, 7 to 8. I said 4.
Sorry. Plug 4 into here, spits out 7. Into here, spits out 8. So now, 4 instead of going to 5, 4 now goes to 8. 4 now goes to 8. So it's like you took this arrow right here, and you now stuck it right there. And now 7
Goes to 4.
goes to 4 goes to 5.
Oh.
You see what happened?
Yeah. Okay.
So that's the intuitive sense as to how that transposition is turning two cycles into one cycle. And then similar thinking down here. So before, 7 went to 5, right? But now let's look at it here. Well, let's look at 4 here. So 4 down here goes to 8. Plug it into here now, though. 4 goes to 7 goes to whatever 7 went to. So now you're breaking it off. Instead of 4 going to 8, you're like short-circuiting it. 4 is now going to go to 5, and 7 is now going to go to 8. Is what that's doing.
Okay.
So it's like, on this one it's short-circuiting it, and then on this one it's combining it. And hopefully it makes sense to you that the numbers we actually used here makes literally no difference.
Yeah.
And these cycles could have been small or they could have been big. It makes absolutely zero difference. So I just wanted to do an example rather than writing out a proof with all the notation that I was afraid you guys would get lost in.
Probably would.
And you can look at the book, because the books can do the same thing, but they'll put in all the notation. Anyways, so that's the idea. So the idea is when I have a permutation and I compose on a transposition, I either combine two loops into one loop, or not loops, cycles. I took two cycles and combined together into one cycle, if the two elements in transposition were already in opposite cycles. And then if they were in the same cycle, I short-circuited that cycle into two different cycles. So we either added one cycle or we took away one cycle from the from the permutation. Does that make sense? Okay, that's what we're trying to demonstrate here. So take a permutation, compose it with a transposition, and you either added one cycle or took away one cycle. Those are the only options. Okay. So now one more piece of notation that we're only going to use for the remainder of this class, and then it's never going to be used again, and that's C of pi. It might come up again. I'm not sure. I should say that. I don't think it will come up again, by the way. So given a permutation pi, C of pi is the number of cycles in pi. So if C of pi is 2 up here, C of sigma is 1, C of pi over here is 4. What about C of the identity? How many loops are in the identity permutation?
Well, let's make
N. Wonderful. That's a good question. Okay. So C of iota is always just N, however many elements there are, because everything just loops to itself. So, given a permutation pi, C of pi is the number of cycles in pi. So another way of restating exactly what this proof says that C of pi composed with a transposition is equal to C of pi plus or minus 1. So the transposition, composing it with the transposition, either added one cycle or decremented one cycle. That make sense? Okay. Now, here's the proof I skipped earlier in the book. Here's restating it. Here's logically equivalent information, so let's make sure they will make sense. Start with what we skipped. So now, if pi is a permutation, can be expressed as tau 1 composed with tau 2 composed with all the way up to tau a, and it can also be expressed as sigma 1 composed with sigma 2 composed with all the way up to sigma b, where these are all transpositions and these are all transpositions, then A and B have the same parity. In other words, A and B are both even or odd. So if I can represent pi as these transpositions and pi as these transpositions, in both cases I represented it as an even number of transpositions or an odd number of transpositions. Does that make sense? Okay, that's what this is saying. This is saying the exact same thing, so let's make sure that we can connect this to this, and then we'll continue with the proof. Alright, so if pi is a permutation, and pi is equal to these transpositions, all the way up to A, then A is congruent to n minus the number of loops on pi mod 2. Now, not loops, cycles. The point here is that it's a constant. This is a constant number, no matter how you represented this thing.
Right.
So we're saying it's a constant, and A is always going to have the same parity as that constant. Notice if A is equivalent to something mod 2, what does that mean? They're either both even or both odd. That's what it means to be equivalent mod 2. Right? So we're saying that any permutation in S of n saying it that way, I'm going to lie. I don't know how else to say it than like this, so let's just say it this way. So if I have a permutation S of n, and I can represent that permutation as A transpositions, then A is going to be equivalent to n minus the number of cycles it has mod 2.
So what was the point sigma up there?
This was if you have two different transpositions, they have the same parity. This one is saying any transposition will have this parity. Two transpositions have the same parity, any transposition has this parity. You see how those are saying the same thing?
Yeah.
Because this is a constant. Once you give me the permutation, I can calculate what this is, and it's odd or even.
It's not. So it's not really like the transposition. It's the number of transpositions that make that permutation, right? A is the number of transpositions.
Yes. A is how many transpositions it took me to recreate that permutation pi.
Right.
So, however many transpositions that'll take me, it's always going to be either an even or odd number.
Right.
So once I have my permutation, I can calculate what this number is, which will be odd or even. And then once I have that, then all my different ways of representing that permutation as transpositions will have that same parity on counts of transpositions. Sorry, that was not a good way to say it. But if this comes out even, then anytime I represent as transpositions, there'll be an even number of transpositions. If this comes out odd, then anytime I represent this as transpositions, it will come out odd.
Okay.
Let's look at an example real quick. So let's look at this one. What was n on this?
N?
Yeah. It's just 5.
Yeah.
Whatever number that is. So n is 5. How many cycles does this have?
5?
This only has 1 cycle.
Oh.
1 goes to 2, goes to 3, goes to 4, goes to 5, goes to 1.
Right.
So this has 1 cycle, and n is 5.
Okay, yeah.
So n minus the number of cycles is 4 is an even number. So anytime you represent it with transpositions, you're going to represent it with an even number of transpositions. Let's look at another one. Let's look at this one. n in this case is 11. How many cycles does it have?
4.
So 11 minus 4 is 7 is odd. So we better have an odd number of transpositions. 1, 2, 3, 4, 5, 6, 7. Yep. So anytime we can represent this thing as a composition of transpositions, it's going to have an odd number. So that's what we're saying here. Does that make sense now?
Yeah.
So any set of transpositions you have, if there's a of them, I know that a is equivalent to n minus the number of cycles on 2.
Okay.
Or a has the same parity as n minus the number of cycles. So let's go through this. So let pi be any random permutation, and assume that pi can be represented as these a transpositions. Okay? Now we're going to consider, make sure that this makes sense, we're going to slowly rebuild pi. So we're going to start out with the identity, and then we apply the first transposition, which just gives us that transposition. And then we apply the second transposition. And then we apply the third transposition. And we keep applying these transpositions all the way until we get pi. You with me?
Yeah.
Okay. So remember, applying a transposition changes this by plus or minus 1, right? So here we're going to write out this list of permutations working our way up to pi. And over here we're going to write out what n minus c of that permutation is. Okay? So here's permutation. Here's n minus the number of cycles in that permutation. So let's start out with the identity. How many cycles does the identity function have? How many cycles does the identity have? N. So n minus n is 0. Does that make sense?
Yeah.
Because the identity function, 1 goes to 1. That's a whole cycle. 2 goes to 2. That's a whole cycle. N goes to n. That's a whole cycle. So the identity function has n cycles. So if I do n minus the number of cycles it has, for the identity function, it's 2. Okay. Now composing the transposition on it gives us plus or minus 1 cycles. Well, there's no such thing as a negative 1 cycle permutation. So in this case, we know it's just 1. Does that make sense?
Mm-hmm.
All right. Next, apply another transposition. That either added a cycle or took away a cycle, right? That's what we proved over here. Anytime you have a permutation and you add a transposition onto it, you either added 1 cycle or you took away 1 cycle. We rewrote it down here. Previous proof says when you compose it with a transposition, you get the same number that you did before, plus or minus 1. So when I add a transposition, I plus or minus 1 to this count. When I add another transposition, I plus or minus 1 to whatever I had before.
As long as it doesn't get negative.
As long as it doesn't get negative, but turns out we don't even need to care about that. The point is, once I get all the way down to pi, how many of these 1s do I have? I have A of them. Right? When it was one transposition, we had one. When it was two transpositions, we had two. When it was three transpositions, we had three.
Right.
When we get all the way to pi, which is all A transpositions, there's going to be A of them.
Right.
Now, I start out 1. Is that even or odd?
It's odd.
It's odd. Plus or minus 1 is even. It doesn't matter. If you take 1 and you add 1, you got even. If you take 1 and you subtract 1, you got odd. Or even.
Do that.
So, we got odd. Once we plus or minus 1, we're guaranteed to have an even. Once we plus or minus 1, we're guaranteed to have an odd. Once we plus or minus 1, we're guaranteed to have an even. And so, the parity of this thing is the same thing as the parity of A.
Okay.
Does that make sense?
The parity of the number of terms?
Add up all these things, whatever it is.
Uh,
Doesn't matter what combination you use of plus or minuses. If there's an even number of terms, you're going to get an even number. If there's an odd number of terms, you're going to get an odd number.
okay.
Does that make sense?
Yeah.
So if there's A terms, then when this comes out even, A comes out even. And when this comes out odd, turns out A was odd. Does that make any sense? Keep track of what this was. This was n minus the number of cycles. N minus the number of cycles has the same parity as A. That's what we were trying to prove. There's a lot going on. So let's talk about this one more time and then re-go over that. What's this one saying? For any permutation you have, if you compose a transposition on there, you either added a cycle or you took away a cycle. Those are the only two options.
Right.
So in other words, the number of cycles on a permutation composed with a transposition is equal to the same number of cycles plus or minus 1.
Right.
Either added a cycle or took away a cycle.
Mm-hmm.
Okay. So now we have pi, which is represented as these A transpositions.
Okay.
So A transpositions, put them all together, you get pi.
Right.
Now we're going to look at slowly working our way up to pi, like we're building our way up to pi. So we're going to start with just the identity function, and then we're going to take the identity function and compose the first transposition with it. And the identity composed with anything is just that thing, right?
Uh-huh.
So start with the identity. The identity composed with the first transposition is just that transposition. Then we're going to compose on transposition 2. Then we're going to compose on transposition 3, all the way up until we get back to pi. And I'm listing those out right here. The identity. The identity composed with the first transposition. Then compose on the second. Then compose on the third. Then compose on the fourth, the fifth, the sixth, all the way until we do all 8 of them and we get down to pi. You good with what this is representing?
Yeah.
Building back up to pi from these transpositions. We know that pi is equal to all these transpositions. It's like saying pi is equal to 1 plus 1 plus 1 plus 1 plus 1. So we're working our way back up to pi. We need to add all these things together, and that's when we get pi. So we're working our way up to pi, and we're keeping track of this number as we do it. I don't know, is that a bad analogy? No? Yeah? You don't know? Still lost? So,
It makes sense, but not like perfect sense, you know.
So start out with what this number is, n minus the number of cycles when we're talking about the identity function. The identity function, everything's its own cycle. 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4. If you talk about the identity function, how many cycles does the identity function have? N of them.
Right.
So n minus n is 0. Okay. So this number, whatever it is for the identity function, is 0. Good?
Yes.
All right. Now let's do our first transposition. Using this theorem over here, taking a transposition and adding it on to the identity either adds one cycle or takes away one cycle.
Yeah. You can't
Right?
take away from 0.
And you can't have a negative cycle permutation. That doesn't make any sense. You can't have a permutation that has a negative number of cycles. So,
You can't really have a permutation of 0.
well, here's that's not the way I should say it. I can't, because in order for this number to be negative, I have to have more cycles than I have elements. That's what that means, if this comes out negative. I can't have more cycles than I have elements, so this can never be a negative number, whatever.
Right.
So it starts out a positive number. So I know in this case, adding a transposition to the identity element always took away a cycle.
You gave it a second.
Took away.
Oh, took away a second.
Took away a cycle, so this became smaller. Right? With the identity, I know that the two elements of my transposition had to be in separate cycles. So I was combining two cycles to make one. Because every element's in its own cycle. I can't have two elements in the same cycle because every cycle is just one element. So when I applied transposition to the identity, I guaranteed took away a cycle. That's the right way to think about it. So this is now one smaller than it was before. So now the whole number is one bigger than it was before.
Right.
Does that make sense?
Yeah, it does.
Okay. Now, from there on out, we're not going to keep track of if it goes up or down, that doesn't matter. The point is, when I add on another transposition, I either added a cycle or took away a cycle. So I either made this number one bigger or one smaller. Add another transposition, made it one bigger or one smaller. Add another transposition, made it one bigger or one smaller. Once I add all the transpositions, all A transpositions, I have pi. Right? So that means I have A of these terms. Right. Okay. Now what do all these add up to? Well, all we really care about is do they add up to an even number or an odd number? And if there's A terms, or if there's an even number of terms, then we're guaranteed that they add up to an even number. And if there's an odd number of terms, then we're guaranteed they add up to an odd number, even though we don't know what that number is.
Right.
So if A is even, the sum of these terms is even. If A is odd, the sum of these terms is odd. The sum of these terms is n minus the number of loops.
Right.
So if n minus the number of loops is even, A is even. If n minus the number of loops is odd, A is odd. Right?
Right.
That's what we're proving. They have the same parity.
Okay.
So that's why I continue saying it. Observe that if that sequence, is even if there is an even number of ones and odd otherwise. Right? So n minus the number of cycles has the same parity as A. Or in other words, A is congruent to n minus the number of cycles mod 2. So now we can calculate the sign of a permutation really quick. The sign of a permutation for any permutation is just -1 to the n minus the number of cycles. Because it's even, if A was even, sorry, the sign of pi is 1 when it's even and -1 when it's odd, right?
Okay. Right.
Back to here. So we know that the sign of pi is +1 when it's even and -1 when it's odd.
That's just how many.
And this is
that's
the
how
same
many
as the number of terms,
transpositions.
or it has the same parity as the number of terms. As a number of, not terms, but number of transpositions. It's a lot to take in. Permutations are really unintuitive. The homework for these is going to be really simple. you're probably looking at this and being terrified, but the homework should be pretty straightforward. I picked really easy problems. I didn't expect you guys to follow everything with this because it's really abstract. But the main purpose that I wanted to for sure cover this chapter was so that you get really comfortable with functions. It's like push you to the next level of just wrapping your head around permutations so that functions are no longer an issue.
Permutations show up more later.
Permutations show up in algebra a lot. I'm not sure if they come back when we do algebra. I think they do. I know that they come back in questions in the algebra section, but I don't know if they formally come back like you had to have covered permutations to cover the algebra chapter. So that's permutations. And that's the last section for chapter 5. So from here on out, you can use the rest of class to do homework, get ready for your test next week, what have you. And then obviously I can answer any questions.